whenever you're ready, Angie, the floor is yours.
Okay. All right. Thank you, Erica. Thank you, Nadina, for inviting me to come and talk today. I'm going to talk about 3 teaching experiments that I did with students who have been identified in the United States as having difficulty with mathematics, and each having difficulty for different reasons. I want to start with this quote because I love that this quote emphasizes how cognition and emotion and the learning environment all influence the outcomes for students and their learning. And it's something that I try to consider throughout the teaching experiments, how the interaction between the person and the environment is influencing what results. So in my presentation today, I'm going to talk about just a little bit about my perspective. It's a little bit unusual for the United States. There's a few researchers in the US doing the work in the way that I am, about what teaching experiments are and what happened in these 3 teaching experiments. What I think the findings from those experiments tell us about individualizing instruction for students with special needs, and a large number of further questions that I think that as a field that we can address to improve the experiences of students. So just to start off with my perspective, as Erica already told you a little bit, I have worked with students who have special needs in a whole group, in general education settings, small group intervention settings, and one-on-one. And my background is in math education, but I have worked on some research projects that involved evaluating instruction for students in special education settings. But in the work that I'm doing now, it's much more qualitative and exploring the learning of students themselves and what's happening, what they're thinking, what their reasoning is. And because I'm doing that as part researcher, part teacher, it's common in qualitative research to try to bracket yourself out of a study. But in a teaching experiment, you as the teacher are part of this study. And so across the bottom, I just have a little quote there from Connolly and Clendenin about the importance of knowing your role as a teacher as you do the study and considering it in the findings themselves as well. So when I do these studies, I try to find out a little bit about the students who I'm going to be working with, and then do some background research on what might be the sources of difficulty for them. Are they the domain general processes like executive functioning or processing or working memory? Are they specific domain, specific to the domain of mathematics, like as in, is it a calculation or a problem solving? Is it related to visual spatial reasoning? And do a little background on what we know right now, background research on what we know right now about those sources of difficulty. We also are going to have a student today who has some issues with anxiety. And so my goal when I start any teaching experiment is to learn as much as I can about the student and as much as I can about the cognitive research right now in those areas, and see how that might be affecting their responses in the instructional environment. But another thing that I do, and another part of my perspective, is that in the United States we have mathematical proficiency tends to be defined in these 5 ways. And most of our research in the US has been done on the first bullet in procedural fluency, because that's the easiest one to measure. So a lot of times the research that I just described in relation to mathematics learning is focused on procedural fluency, but we also want to support conceptual understanding. And I'm particularly interested in adaptive reasoning and productive disposition, and how we can support those proficiencies in students who are experiencing difficulty in math. So taking the cognitive science research and these goals that we have currently a debate in the United States that's intensifying at the moment about how we should deliver instruction. And we tend to have agreement here that systematic instruction is useful and beneficial for students, connecting to their current knowledge, making sure the representations that we're using are accessible, the number sets are accessible, and very systematic, gradual increase in complexity. But the disagreement is around a couple of instructional delivery methods. And explicit direct instruction is dominant here in the United States in intervention settings for students who need support in math. But there's a small but growing number of people arguing that we should be building on student thinking through problem solving and reflecting on activity. I can talk more about that if you're interested, to address those proficiencies such as adaptive, strategic flexibility, adaptive reasoning, and mathematical proficiencies. So there's an opportunity. I'd be interested to hear what your positions are in your countries on this debate and whether or not there's agreement for you in your work. Another piece of the work that I do, so there's several pieces of this puzzle that I'm trying to put together, is the research on cognition, the proficiencies, what are the instructional strategies we can use, and another one is learning trajectories. And I'm defining learning trajectories a particular way. If you're familiar with these, they can be defined in different ways. I'm just talking about a developmental progression, a sequence of learning goals and tasks that are aligned to those goals to move students along the progression. And by that progression, what I mean is the ways in which mathematical ideas develop over time. So particular mathematical content and how individuals come to understand that content as they're exposed to it over a period of time. It can be over a few months to a couple of years, depending on the progression that you're studying. And some of the progressions that I have been drawing on also involve ideas like cognitive processes that are perhaps drawn upon consistently as they make progression in the mathematical understanding. So that might be processes like generalizing or making connections across representations, or doing specific mathematical transformations. So cognitive processes and the development of ideas will come up a little bit in the findings. So I want to touch on that, but I'm happy to answer more questions if needed to make the findings make sense. I don't want to spend too much time on it unless you're interested. And then one of the reasons why I'm interested in exploring learning trajectories is there's some initial studies that show there have been positive outcomes for young students with at risk for difficulty. They've been found to be supportive of executive function in whole group and whole class instructional settings. They do offer opportunities to build on student thinking, but they also, using this instructional approach, there's also the opportunity to use direct and explicit approaches and sort of compare the effects of the direct explicit instruction and the building on student thinking. And we also, there's a need to do this because they're having more and more impact on curricula in the United States. There's very little knowledge about the developmental progressions or the learning trajectories for students with special needs. So I'm going to pause there and see if, because I know I went pretty fast right there through several slides about the background and the way I've approached these teaching experiments, to see if there's any questions or comments.
So far, there are no questions on the chat.
Okay, all right. Okay, so the three teaching experiments that drew on those perspectives are, I'm going to talk to you a little bit about three students, Eva, Miranda, and Macy. And they all have different needs, but first I'm going to tell you a little bit about the methodology that I was using to study their learning. So the teaching experiment methodology, just a quick overview for those who might not be familiar with it, it's typically qualitative, though you can include some quantitative work in it. It's a study that's done in a natural setting, in an actual teaching and learning setting. That's more typical of instructional practice. So you're not able to control variables in the ways you might in a laboratory type of study. It's a very cyclical process where you implement some instruction, observe, gather data, do ongoing analysis and refine your instruction, and then implement again and try it out again. And keep going through this to maximize the benefit for students as you do it. It's a methodology that also lets you really focus on what students are thinking, understanding, rather than simply on the outcome on an assessment. It's also designed to respond to student thinking. So if you find one thing's not working, you are able and obligated to adjust and do something that's more beneficial to students and document those decisions. But you do focus on something. There's something that you're focused on within the method and within the teaching. And that focus is usually around what we're calling a local theory. So rather than a broad theory such as social learning theory or constructivism, we're focused more on a specific theory about learning a particular mathematical topic. And the procedures within the teaching experiment, there's two approaches. The first one is typically an exploratory phase where you are giving students some math tasks and just observing how they respond to it and trying to understand their initial ways of thinking. And then based on your observations, you develop a hypothesis for 1 to several sessions and test that hypothesis over time. Another approach is that you begin with some sort of guiding. It's not quite a hypothesis. It's a conjecture, or something that you think might be true, and you continually test and revise that conjecture over time based on what students do. In my study that I'm presenting today, they all use the second approach of the guiding conjecture, and we'll talk about what that was in a moment. The data sources are typically, you record your planning sessions and all your documentations for planning that include your rationale for decisions and what you think is going to happen. You collect video of the students' activity, students' work samples, and then you reflect on all those recordings and documents in the next round of implementations. As I mentioned, it's a cyclical process, so you analyze all of this data in an ongoing way. And then once the study is over, you do a retrospective analysis. I used a couple of different qualitative methods of retrospectively analyzing the results of the experiments once they're entirely done. And you usually do that just to inform the broader theory, or to start seeing how the results from this particular experiment might generalize to other students. And the analysis is really beneficial to have multiple researchers involved in that analysis. However, these studies were done during the COVID-19 pandemic. And with each of the students, I worked with them when local quarantining requirements allowed for it. So not all the studies were allowed or involved multiple researchers. The study with Eva is an exception. There was another researcher involved in that one. Okay, so the conjectures was the approach that I took, and I was exploring the use of a learning trajectory and how a learning trajectory might provide the systematic instruction that these students needed, but give us the flexibility to individualize. And one of the goals was to identify what another person has referred to, and I put it in quotes because I don't know if it's a common phrase or not, the precipitating events, the things that actually happen that support, or those moments that really supported, make a difference in the students' learning for students who have difficulty in math classes. So the first study I want to talk about with Eva had some pretty intensive learning needs. Eva was identified as having generalized anxiety disorder, a speech sound disorder, mixed expressive receptive language disorder and attention deficit hyperactivity disorder. She had developed, at 9 years old, she had already developed a pretty intense dislike of mathematics. And she would quit when she didn't know what to do, immediately quit. If she saw the task and didn't recognize what she was supposed to do, she would quit. She'd get up and leave the area. Or she'd get angry when she was pushed to do something, and she rejected suggestions from the teacher. So one of my goals was to see how can I best support her essentially engaging that productive disposition of the 5 proficiencies to support the productive disposition, something that would keep her in the learning environment. And her mathematical skills in arithmetic were considerably below grade level, and showing her anything with numbers really triggered that anxiety. So we focused on geometry and spatial reasoning, and a particular learning trajectory that showed a lot of progress for her was the 2D shape composition trajectory. This is it's defined as gradually developing understanding of and attending to geometric attributes and mentally anticipating the results of combining shapes. So essentially, in the first picture on the upper left, you can see that she's creating a diagram in which each of the tiles or shapes plays a unique role in a picture, and she doesn't combine shapes to create a composite shape. And through a really gradual systematic increase in difficulty, the second picture shows how I was giving her puzzles and tasks that she would find accessible in the beginning, that she wouldn't jump up and run away. She might recognize right away that she had a solution path. By gradually increasing the difficulty of those puzzles, she did stay involved in the tasks and became all the way through to the last picture, where she's starting to combine shapes in different, or combine the tiles in different ways to create the same shape. Hopefully you can see some parallels to numerical ideas in here, like composing numbers and decomposing numbers, or finding and making quantities in making a total quantity in different ways. We didn't address those number related issues, but they were the ideas of composing and decomposing were central to this trajectory. One of the things that I found, in addition to the gradual systematic instruction supported her confidence and her perseverance, was that the more language I used and the more direct teaching or questioning I did, the more likely she was to reject the task and leave the area and not want to perform anymore. So I found in this teaching experiment that the really independent, individual, gradual tasks were what supported her learning the best. The second student that I did a teaching experiment with is Macy. Her difficulties were in executive functioning, abstract reasoning, and expressive language. And the challenges for Macy that I knew going in was that she learned things very slowly. It was a process of a lot of repetition, a lot of practice, and she struggled to connect ideas, maybe related to her difficulty with abstract reasoning. With Macy, we were working on an equipartitioning learning trajectory. This is a learning trajectory that supports fraction understanding, but also ratio and function by making equal-sized groups. And I have a few pictures here of her work. She was, in the first pictures, working with a pirate's treasure. The pirates had 12 coins, and there were 4 pirates on a ship. How many coins would each pirate get, and what size of the whole treasure would each pirate get? And distinguishing between those two quantities was a bit of a challenge for Macy. There was also, in the picture on the right with the fraction strips, those were a giant French fry, and a different number of people are going to share this giant French fry. And I was trying to get her to anticipate the size of the share as more people were sharing. And she was pretty good at estimating that. She really struggled again, though, with the idea that denominator was telling you that the larger the denominator, the smaller the share. She saw that as that the larger the denominator, the more sharers there were, but making that connection to the size of the share was very difficult for her. And then there's a picture of her fractions understanding, and I just wanted to show that because she recognized 1/4. In the 1/4, that's a circle diagram, she drew those lines in to make sure that what the shaded area was 1/4. You can see there's some faint lines in there. In the bar that shows 1/3, there was a bar that shows 1/3 and a bar that shows 2/3. If you look at the dark shaded areas, she named them both as 1/3, and was so one of the things I wanted to point out was that her view of representations, the way she was reading representations, was maybe not the way that I intended her to read them, and it was something that I had to really pay close attention to. So, but the major findings from this study were that very subtle variations in tasks with really clear connections between the tasks were really necessary for her to make those connections, and that she understood denominators that were as quantities and not as shares, as the size of the share. That in all these cases that the denominator was telling you how many parts there were, not the size of the parts relative to the whole. The third student was Miranda. Miranda had attention deficit hyperactivity disorder with particular difficulty in inhibiting behavior and sustaining attention, and she compromised accuracy for speed. She wanted to be done with things. So those were the main challenges. How do we keep her moving forward toward a complex goal, and how do we get her to attend to accuracy? I also worked on the equipartitioning learning trajectory with Miranda, and I have 5 quotes here from her about what it was like to do these with her. She would say, "I'm so confused," and then she'd say, "No, really, I'm bored. I'm bored to the extreme." So it wasn't really that she was confused. She decided, that's not it, I'm bored. And then she'd say, I've heard that I'm hard to work with. It's my environment. There's so much going on around me. I'm an excitable person. But when something really intriguing happened to her, she would say, "Mind blown," and she would get very excited about it. If we have time or interest, there's a short video we might be able to show of her working on a task. Miranda had very little interest in the subtle variations of tasks that were necessary for Macy to see connections between things. She did not want to repeat it. She had no interest in it. She did not want any teacher support. And like Eva, she did not want teacher support. She did not want the teacher talking to her, interrupting her thinking. The best thing to do was to engage her in challenging tasks, help her document or notate things, and just plan a very few limited purposeful questions ahead of time that might direct her attention toward the big idea very quickly. So that is, I wanted to give you a brief overview of these 3 students. I'll pause again there before I get into the implications of these 3 studies and see if there's any questions. Don't see anything in the chat yet. Okay, so here's what this comes down to. What have I learned from these 3 teaching experiments about individualized instruction? So for the learning trajectories, Eva's trajectory was very closely aligned to the hypothesized trajectory, but she only showed progress when you use that really systematic gradual increase in difficulty. Macy's trajectory, we might say, was in the same conceptual corridor. She didn't really align very clearly to the learning trajectory. There were these levels 4 through 6 where she sort of had pieces of this trajectory, but that understanding about denominators not as a size as a quantity was preventing progress in those areas. So once you address that challenge of understanding, all of those things might come at once. in her trajectory. And Miranda moved really steadily through this learning trajectory, through that developmental progression, without much holding her up, as long as you just could sustain her attention. So what I think this means for individualizing instruction is that the learning trajectories did enable the instructional pieces to be responsive to students' ideas. I didn't have to follow them in lockstep, but sometimes I could follow them in lockstep because of the students were showing understandings in those ways. But the issues with Macy showed that I could be responsive to her and still support her learning, but use this framework as a way to structure the lessons. But the challenges with the learning trajectories is that it really took careful attention to their student thinking. And in a classroom environment, that might be really difficult if there's a number of students to provide that kind of careful attention and ensure that you are attending to their thinking. And also, in particular with Macy, her responses were correct in some tasks and in some levels of this learning trajectory, but in others, they weren't. And that was related to that underlying way understanding she had about denominators. And so that can also be a problem if you're using learning trajectories in instruction, that you might assume that students understand something that they really don't, and that they're not ready for a higher level in the progression, but the task that you've given them isn't revealing the limitations of their understanding. I mentioned also that the value of learning trajectories was that it let me compare direct instruction to problem solving. And so I want to talk about how these showed up in these studies. That direct instruction did not sustain attention for Eva. She did not want that kind of guidance. I suspect that was related to her language processing challenges, and that by struggling with receptive and expressive language, it was increasing her anxiety, and she was rejecting the learning situation. Macy did respond quite well to direct instruction and corrective feedback, especially when that guided her to pay attention, like in that 1/3, the two representations that show 1/3, direct instruction on what she's supposed to attend to in those representations was really useful and worked quite well for her. But that did not mean she would transfer it to a new context. You needed to continue to make those really connections clear. As if I changed from the bar representation to, say, back to a circle, I would have to make it clear that it's the same rules, the same naming conventions that apply to the different representations, and help her practice applying them across those settings. But then again, Miranda was not interested in direct instruction. She was not interested in accuracy, and she wasn't going to stop to listen when you tried to teach something. So the affordances of the direct instruction were that it did help correct errors when those errors were interfering with developing understanding. But for 2 of the 3 students, it didn't sustain their attention. They weren't interested in listening. And it didn't really support because of that, it wasn't supporting their development of understanding or of reasoning. Direct instruction in the United States is considered opposed to problem solving. Maybe in reality they shouldn't be, but those are considered 2 contrary approaches in the United States. And Eva could engage in problem solving and struggle with things when you gave her really, really minute changes in the difficulty. And that did support her perseverance, but it took really careful planning and really careful watching of her to see what's the right next step, because if you went too far ahead, she'd reject the task, she'd give up very quickly. Macy readily engaged in any problem that you gave her. She was very agreeable to all kinds of instruction, but problem solving alone did not support her in making any connections across tasks. It needed to be supplemented with that really explicit instruction that directed her attention. Problem solving was the most effective method for Miranda, because if you gave her some sort of a challenging task, without a ready answer, she would find it intriguing, but she needed to be able to solve it fairly quickly to sustain her attention. So problem solving was something that was more motivating for students. There was more evidence that it was supporting conceptual understanding and adaptive reasoning. And I would add the productive disposition. But the constraints were that it was very difficult to find the right amount of challenge for each of these students to keep them engaged. And in that problem solving, Macy in particular struggled to see the mathematics. She would do the problem solving, but didn't pull out the mathematical ideas that we were looking for. And time would be needed for these students to really use that problem solving in a effective way to get the outcomes that we're looking for all those proficiencies. So pause there and say, are there any questions about that? I don't see anything in the chat. All right, so I'm transitioning now to essentially these teaching experiments were designed to be exploratory, to find out what happens when we use learning trajectories and think about why direct instruction might be working or not working, why problem solving might be working or not working. And they provide a lot of description of the learning, but they also lead to a lot of additional questions. So Eva in particular had difficulty with language-rich mathematical tasks of any kind. And what would we do to support a student like Eva in a language-rich mathematics learning environment? A lot of math instruction in the United States right now is heavy in discourse and language. And so what can we do to support a student like Eva who showed much more progress when she could just be left to figure things out on her own? For Macy, the ability to pull out the mathematical ideas, she can get answers right in certain contexts, but there's a lot of evidence that she's not getting the underlying mathematical properties and relationships. How do we help them make those connections or see the mathematics that's underlying the representations that we use, like the bar 1/3 and 1/3? How do we make that evident for Macy? How do we draw on her strengths in willingness to solve every problem, but draw on that in order to help her overcome those difficulties of connecting things? And Miranda, it was questions about how do we do this intriguing problem solving, things that really inspired her, but also demand attention to precision and accuracy. How can we support that in a student with more challenges in sustaining their attention and inhibiting distractions, in particular in whole class learning situations? And then there's also just the questions about learning trajectories, like which progressions, developmental progressions, are supported by primarily scaffolded approach that we used with Eva, and which progressions would be supported by direct instruction, and for which students, and how can we use that if learning trajectories are guiding our curriculum in general education settings? How can we adapt that to the students' particular needs? So just before I present my long list of final questions, I just want to go back to thinking about this quote, that the opportunity to learn is this relationship between the individual and the environment. These are the questions that I think I would love to explore, or love to see other people explore related to opportunity to learn. So the developmental progression, how do these ideas develop in students who have different cognitive and affective resources? We can't assume that they develop the same way those ideas develop for us or for typically achieving students, but we also can't assume they're different. So what are they? In what ways are they variable? Are they variable in the way they learn the mathematics, or are they variable in those cognitive processes of reasoning and connecting that are needed across no matter what point in the development of ideas you're at, and for which students? And then what are the relationships between the cognitive processes and a learning trajectory? how can you best support, when should you best support, and when can you allow students to engage in the tasks on their own and rely on their own reasoning and develop the ability to reason and develop a productive disposition. And I think that issues of direct instruction versus problem solving are, I think there's a balance to be had in there, and it's a decision about when and what sort of intention you have behind each of them and when you're drawing on it, and how can we teach that balance to teachers so that they can draw on them too. I think we have to better understand it ourselves before we ask teachers to try to implement it. And then how do we, I think the issue of access to mathematics when students have difficulty with language or understanding representations or sustaining attention, what can we do to support their areas of relative weakness? How can we draw on their strengths so that they can engage with the mathematics that we're using in schools that is heavy on all of those things, heavy on language, heavy on representations of abstract mathematical ideas, and heavy on the need to persevere and pay attention and sustain your attention through a complex process. So maybe some of these questions are not new to you, but I think that the teaching experiments that I did give me a new lens on thinking about what they mean and what maybe some paths for further exploration are. And I would love to hear more about what questions you have about teaching students with special needs in mathematics, and answer any questions you have too.
Thanks a lot, NJ. That was amazing presentation. Yes, you can see some claps. I think you raised a lot of very interesting questions here. I think I will leave some time to the participants to think about all the things that you shared with us. That was really, really fascinating. So anyone that wants to ask question or join the discussion, you can switch on your camera and your mic and just ask the question, or you can type it on the chat. And while we're waiting, I would just start by saying that for me, it was very fascinating listening to you talking about teacher experiments. This is really great methodology. And I think should be known a bit more. I think you're really brave in using and using this, because it is really complex methodology. And I don't know if it is just a different label, but I was familiar with something that is called action research.
Mm-hmm.
Is it something similar? Is it different from what you do?
It's similar. Action research is similar. I think that the teaching experiments, I would like to see more people do teaching experiments, because they are, one thing I find the most challenging is writing them up for publication, because they are so complex. There's so many things that are going on, but I think they also give us insight into what happens when we, I had that slide in there about like doing the background research on, domain general and domain specific processes, and what do we know about that. But what happens when you try to take that, what you've learned about that, and design a task that draws on the research, but do that with a student in a math situation. These were one-on-one situations. You can do teaching experiments whole class too, and I think there's a real need for that, to see how are these students responding in the actual classroom environment. And I think what it'll bring out is that there's a lot of challenges, a lot of contributing factors that we have to try to figure them all out in order to support their learning. Action research is very similar, because it involves also that really naturalistic setting you're doing that work in the setting with the students. It is less often that sort of cyclical process. It's often got, you have a hypothesis, you test it out in the classroom setting, and you collect data and you see whether your hypothesis was found to be correct or incorrect. Whereas a teaching experiment is more about, well, we think this might work, and if it doesn't, we're going to change it in this way. And if it doesn't, we're going to decide what else needs to be changed, and you continue. So it's more like design research in that way, but they are similar.
Yeah. So I was mentioning a lot of, you put a lot of new content here. So this teaching experiment was one, but also another interesting discussion would be about the learning trajectories.
Mm-hmm.
There's a lot that can be said there. And one thing I was thinking about was how much previous experience might have influenced the learning trajectory of a student, and how can we measure that? Or do you try to measure it? Do you that was just something that I was thinking while you were talking about your three case studies.
You're right. I went very fast over learning trajectories, especially considering that's what the focus of each of those studies was. But I think you said their background knowledge. Is that what you were talking about? The
previous experience.
Previous experience
Of the student.
Yeah. So one of the reasons that people in the US, I was just at a conference where learning trajectories was the keynote speech. We were talking about it. One of the reasons it's, I'm interested in exploring it with students who have difficulty in math is the idea that it is supposed to, you find what they're thinking right now. And so you do find it's like very intentional about what do they already know, and then designing the next steps from there. A lot of the learning trajectory research that's been done right now is based on large numbers of students, just a large number of students. How do they respond? What do the ideas seem to be? What seems to be the typical progression? What are the ideas that very young students have all the way up into older students? And looking at them as a progression of concepts rather than a progression of skills. But we don't know which of those, we don't know to what extent students who think differently about mathematics have the same progression, and do they have the same starting places? And that's kind of an unknown. So that's sort of part of motivated this study. Like, could I give them tasks and figure out where they might be in a progression, so that if I was a classroom teacher and I knew I was going to teach this topic, could I use this learning trajectory, and would it benefit all the students? For these students, it wasn't hard to figure out where they were beginning, because they could do tasks that aligned with a certain level and not do tasks that aligned up here. And then when I would ask more information or seek more information about their reasoning in these tasks, you could pull it out and you could figure out what they knew and didn't know. But right now there aren't very many assessments or measures of it. There are some researchers who are developing assessments and measures, but there aren't very many out there. So as they start to develop it for general education settings, I think it's important to think about whether or not those assessments are going to be valid measures for students who have different needs in learning.
Katina, do you have any questions? I see your...
No, actually, well, I have to say I liked a lot the presentation, because we are used to see the more methodological part of research, and it's really nice to see how research sometimes appears more close related to practice as you did. So it's not my area, and maybe that's why I don't have many questions on that, because I need to know more about that. But just thank you for the presentation. I liked it.
I recognize there's a lot in it because, and that's part of the challenge of the teaching experiment. It is trying to connect all these other things to practice and then pull those pieces back out again. And it's very hard to decide what to put in a small box. That's why it's hard to write papers and manuscripts with them. And but I think they're pretty informative, and I think they just raise a lot of questions and things that I think that both people who do research on teaching and people who do research on learning can consider a teaching experiment and come up with a lot of their own questions about what might have caused this or that, or what effect might something else have had in that setting.
Sure, yeah.
I'm going to ask you another question.
Okay.
We have a few more minutes, so and in the meantime, if anyone has any questions, please add them on the chat. I found very interesting what you meant when you mentioned the debate about instruction being direct instruction or problem solving. What I always thought is that it is a spectrum, and sometimes you position yourself most of all of the time you are in the middle of the spectrum, but you are not. It is very difficult to just give a direct instruction or a problem-solving instruction when you are teaching. I don't know if you had the same feeling. It depends, of course, from the intention that you might have, but it is really difficult that it is 100% direct instruction or all the time. It is always a mixture of it, and so I find it difficult to label this and to define this. And I don't know if you had the same issue when you were doing your teaching experiments.
In the US right now, there is a pretty vocal group of people who are arguing for direct instruction almost exclusively. And a fairly large number of school psychologists and special education researchers that are arguing for that.
Sorry for interrupting you, Angie, but for example, if you think about the first study that you were describing, the one with the shapes and the types, an example of direct instruction there would be to say to the student, pick the green tie and put it.
Yeah, right. So
something like that,
or to describe a process,
okay.
Like, so to say, okay, here is a puzzle.
Mm-hmm.
What I want you to do first is the first step is to pick a corner of the puzzle that has something that has an angle you can recognize, right? And so then you match, the next step would be to match that angle to an angle of a shape in the box, a puzzle piece. And so you're telling them, like, you're breaking down the process of filling in that puzzle step by step, what you should pay attention to first, what you should pay attention to second. And
it is very verbal, right?
Yeah, and it is variable. There's different ways of approaching it. And especially with the really simple problems, you know, as adults, we probably would look at it in one way and we're like, this is the most sensible way to start. And so that's would guide our direct instruction. But I was talking with somebody who has done some work with a bunch of young children and that exact same geometry progression. And she said that when they observe it, that some young children start from the outside and work in, and other young children find a block that fits on the inside and work out. And the concern I have about direct instruction is, one, you don't allow the child to decide how to solve the problem for themselves. And two, if they're a child that works in and sees it in some way in their mind as something that you start from the center and you start filling this way, how does constraining the way they see it to something different affect their ability to understand the mathematics? I mean, I'm concerned about that. So I have a lot of concerns about using direct instruction exclusively, and I would prefer to use it more effectively than exclusively.
And on the other side, what would be an example of an instruction for the same task that is problem solving, if we're thinking about the puzzle?
Yeah, so in that trajectory, if you're thinking about it as in problem solving, you can give a variety of tasks. You can give outlines only, or you can give interior lines. You can give shapes that share. Let me see, there was one picture of a house that had, you could build the whole house with squares, and then you could build the roof with the trapezoids. And so you can design pictures that that you give to students that ask them to do a number of things without telling them, which would be combine the same shape in more than one of the same shape to make a single part of the picture, as in all squares in the house, or combine all trapezoids to make this. But you don't tell them that, but the picture is designed to do that. And then at a more complex level, you would design a picture where they'd have to maybe include a trapezoid and a rhombus to make one part of the shape. And you either can combine or not give the anterior line, depending on what level of difficulty they're ready for. So the problem solving involves giving them a geometry task that pushes them to do something they don't do yet, but maybe only one or two things that they don't do yet. In the very first picture, Eva could make a picture with multiple blocks, but none of them shared sides. So one of the things I might want to do is design a task that kind of forces her to figure out that they need to share sides, but not tell her to do it. Did that make sense, that description of problem solving there?
Yes. And
so you're selecting the features of the task to best show that, to best press them to do something they don't do already.
And the difficulty there is to assess where the child is and to develop a task that is challenging just enough, right? So you need to really know the child you're working with, and to really know the topic that you are teaching. And that is very challenging, I can say that. Well, thank you for sharing all of this. I think a lot of food for thought here, definitely.